Runway sledge slides down a slope at a constant speed. One force is shown on the free body diagram of the sledge is the normal contact force. It is the normal contact force of the snow on the sledge. Add to the free body diagram to show the other two forces acting on the sledge. Name each force and state what is producing it or the cause of that force. So remember what I said about free body diagrams. You always draw forces and you start it from the object, and the force will be always pointing away from that object for which you are drawing the free body diagram. For this sledge, we'll have weight acting downwards and we'll have friction acting in the opposite direction. So these are the two forces. Next, we have the sledge slides 15 meters down the slope at a constant speed. The normal force is 40 Newton. The resultant force acting on the sledge. Okay, here I want to point out something which will be used again and again in different questions. It is one of the techniques in questions. Whenever you are reading a statement, you should always look for keywords in the problem statement. Now, in this statement, this constant speed is a keyword, right? Like it has a meaning, and you have to use this word to answer this question. So whenever you are working with forces or kinematics, whenever you see this word, constant speed, or for example, constant velocity, or it is not accelerating anything, that tells you that velocity is constant. That implies that acceleration is zero, and acceleration being zero in turn implies that force or net force is zero, right? So just by looking at this word that the sledge is going down with a constant speed, you can tell that the net force or the resultant force on the sledge will be zero. Last part is what is the work done by the force N, that is the normal force. Now let me draw the diagram here and I will exaggerate the slope of this slide. So if this is our sledge, this is normal force. Remember that normal force is always perpendicular to the contact surface. So as you can see here, it's making 90 degrees angle, and we'll have weight acting downwards. Now, if I draw axis on this, I will draw y-axis like this, and x-axis will be like this. This is also important that whenever you're choosing axis, you should always choose axis such that one of the axes is the same in which the object is moving. As you can see, the object is going this way. So I've chosen my axis tilted from the normal axis that we choose, like this. If I had chosen this axis, the sledge would have been going at an angle like this, and I would not know anything about this. Even if these angles were given, it will be difficult for me to resolve it and then work in terms of the components anyway. So I'll choose this axis, and now you can see that this is normal force pointing along y direction. This normal force has no component in the direction of motion. So that's why work done by the normal force will just be zero. But if you calculate work done by weight, you'll see that weight has one component, which is this one, which is in the direction of the motion of the sled, right? The sledge. So this component of the weight is actually the reason the sledge is going down. But you can ask yourself, if work done by this component of the weight is not zero and it's positive, why is the kinetic energy not changing? And the reason is that the net force on the sledge is still zero. Can you figure out how is the net force on the sledge zero? We have this component of the weight acting downwards, but we also have friction acting in the opposite direction, right? So if you calculate work done by the frictional force and work done by the weight, you will see that both of them cancel each other and the sledge is moving at a constant velocity downwards. So the net work done on the sledge is zero. The work done by normal force on the sledge is zero. But if you calculate work done by weight on the sledge alone, not the net work done, just work done by the weight, it will be non-zero.